All right, more to do with quadratic functions. So more applications here. So it says, what kind of situations are described by quadratic functions? So part A, the equation of the quadratic function that describes this situation is given. So you don't have to come up with any equation yourself. Then we'll look at ones where you do. So these are kind of the easiest. So the first one, a ball is thrown into the air from the balcony of an apartment building and falls to the ground. The height in meters of the ball relative to the ground t seconds after being thrown is given by that equation. How high is the balcony above the ground? So think about it. The ball is thrown into the air from the balcony of an apartment. So let's do a little, there's your apartment. Here's a balcony. Here's a balcony, and it's thrown up into the air and lands, okay, onto the ground. So the path that takes follows the shape of a parabola if the independent variable is the distance from where, horizontal distance from where it's thrown. Also, it does when it's based on t. So this is what it looks like, and really the t value is the time here, not the horizontal distance, but you can think about it this way. So at time equals 0, we want to know what the height is, because that's the initial height. So taking a look, using your function notation, really you don't have to show any work. Because if it's expanded out, this goes to 0, this goes to 0, and you just get 60, which is the constant term. So high is the balcony above the ground. That would be 60, and this is in meters. Although it didn't actually, oh yeah, it did, h in meters. Okay, so 60 meters. Express the equation of the function in vertex form. So that's what we learned yesterday. So there's your equation. Now we want to factor out the coefficient of t squared. Put the constant term outside. Take half of -4 and square it. And add and subtract that. And then -5 times -4 is +20. Okay, so now it's in vertex form. Then it says, what is the maximum height of the ball above the ground? So there's your vertex is 280. So the maximum height is 80 meters. The h value, the dependent value at the vertex. How long does it take the ball to reach that? That would be the t value at the vertex, which is 2 seconds. Determine when the height of the ball is 45 meters. Okay, so that is 45. So h equals 45, t equals something. So algebraically, we would put 45, and I would use the vertex form, so we can algebraically do this. Otherwise, we haven't learned enough to be able to, probably it doesn't factor. So we'll do it this way. That's going to be -35. Divide by -5. I'm going to put the t minus 2 on the left, plus or minus the root of 7. So t equals 2 plus or minus root 7. Okay, so there's 2 times. Well, what makes sense? 2 minus root 7 doesn't make sense. 2 plus root 7, so this is inadmissible. Doesn't make sense for this application. Okay, and so that's going to be, just summarize over here. That will be 2 plus root 7 meters. No, this is seconds. And then let's find the decimal form of that. So 2 plus root 7 is 4.65 if we go to 2 decimal places. We'll do it on our calculator in the set. Determine when the ball hits the ground. So the height when it hits the ground is 0. So now if we do that, it's going to be 0 equals negative 5t minus 8, t minus 2 all squared plus 80. So I'm going to bring this to the left. And 80 divided by 5 is 16, which is nice because that is a perfect square. So the root is 4. So t equals 2 plus or minus 4, which is negative 2 and positive 6. That's inadmissible. So 6 seconds is when it hits the ground. Sketch the function, labeling the axes and vertex. So here, it would look something like this. The vertex we found was 280. The height of the balcony was 60. So this is your H. This is your T. We're not going to graph anything more than that because it doesn't make sense for the situation. When it hits the ground is 6. Okay. Labeling the axes and vertex, we actually did the intercepts as well. State the domain and range. So domain in this case is time. So that's between 0 and 6. Again, just for this particular application. Okay. Obviously, domain for any parabola is all real numbers. Then the height, that's between 0 and 80. Okay. Now, if you wanted to graph this, go to y equals, just put in the original, negative 5x squared plus 20x plus 60. Then your window, we know we have to go from 0 to at least 6, so let's go to 7 based on our calculations. 1 in, go from 0, and we have to go to at least 80, so let's go to 85. And we can go up by 5s. So if we graph that, okay, then trace, let's check 6, enter, 0, that's good. The maximum, so let's closer. You can also punch in a number first and then you're closer already, but do that. Oh, all right, do that. Enter to the right, enter, 280. Okay, that makes sense. You can also look at trace when t is 0, y is 60. That's the height. So we've got it done perfectly. If you wanted to check, remember we had to find the time when the height is 45, and you go y2 equals 45. Then second trace intersect. Enter. So 4.65, which is what we did. We did it algebraically and then converted to a decimal. This is the decimal form. Okay. All right. So next question. This is where we have to come up with the quadratic function. So we want to label the variables, have our let statements, write the equation, and then put it into vertex form and answer the questions. So it says two numbers have a difference of 12. Determine the numbers if their product is a minimum. So anytime you see an application question that has the words minimum or maximum, you know you want to put it in vertex form so that you can see what that minimum or maximum is. Okay, so let's so here, label the variables, okay, and we want to get the product. So let's let X be one number, let P be the product, okay. Here, if X is one number, therefore the other number, you can do X and Y, but then you'd have a third variable, right? So the other number, if they have a difference of 12, so let's say we have X minus some number equals 12. So that other number is X minus 12, okay? Or it could be X plus 12, actually, either way. Write the equation for the variable you're maximizing or minimizing. You may have to do some extra work to get the function in terms of one variable. Yeah, so if you had done X and Y, then the difference you'd have to solve for Y. In any case, I didn't, so my product is X times X minus 12, okay? And I'm going to expand that out. Then it says, express the quadratic function in standard form and vertex form. Write a max-min value statement. So standard form, that's already in standard form. Vertex form, oops, we want to factor anything out. There's nothing to factor. No constant term, so really we're going to take half of negative 12, which is 6, square it, add and subtract. Okay, and then factor that, X minus 6 squared minus 36. So write a max minimum value statement. So here, this is opening up, so the minimum value, and that's a way to confirm, did you maybe do something wrong? Because it asked for the product to be a minimum, and this is a parabola that's opening up, so you know its minimum value is negative 36, okay? Yeah, when X is 6. Now, it says read the question again and determine what was to be found. So it says two numbers have a difference of 12. Determine the numbers if their product is a minimum. It doesn't actually ask for what the minimum value product is. Ask what the numbers are. So therefore, the two numbers, start again. The two numbers are, so one is X, then we put it back into our other statement. The other one is 6 minus 12. Oh, so I meant to say 6 here. And 6 minus 12 is negative 6. If you multiply those together, you get negative 36, which is what you said was the minimum. Okay? So you need to have a let statement. You need to show your function. You need to put it in vertex form, and then a statement answer. Okay? We call that particular example a number type question where you're relating two different numbers together. Next one is a revenue type question. It says the cost of a ticket to a hockey arena that seats 1,000 people is $12, and at this price every ticket is sold. The survey indicates that if the price is increased, for every $2 of increase, the attendance will fall by 50 because it's more expensive, so fewer people will go, but they might still make more money. Determine the maximum revenue and the ticket price that will give the maximum revenue. So maximum revenue means the most money coming in. So we've kind of helped you out here. It says let X be the number of $2 increases, okay? And then in this case, we are trying to maximize R, and R the revenue, R for revenue, okay? So step 2 is coming up with the equation. Before we do that, for these ones, you might want to do like a little chart to help yourself. So the revenue is the price by the number of tickets. All right. So if this says $12, they sell 1,000 tickets. So that would be revenue of 12,000. If they increase the price by $2, then they'll sell 50 tickets less. So what do you get in that case? 14 times 950. 14 times 950 is 13,300. Okay. And so you can see it's more. So we want to figure out what price will give us our maximum revenue. So each time here, so in general, so X is the number of $2 increases. So this would be 12 plus 2 times 1. This is, the next one would be 12 plus 2 times 2. Okay, and that would be for here, this is 1,000 minus 50 times 1. This would be 1,000 minus 50 times 2. So these are your X values. So your general case R is 12 plus 2X times 1,000 minus 50X. Okay, so that's going to be your revenue equation. 12 plus 2X times 1,000 minus 50X. Okay, and so next is to put it into vertex form. So first of all, expand it out. So that's going to be 12,000 minus 6,600x plus 2,000x minus 100x squared. I'm going to put it in descending order of degree and add like terms. And now we want to put it in vertex form. What this is called is completing the square. So when we factor out negative 100, okay, I'm going to take half of 14 is 7 squared is 49. Oop, that's going to be plus 4,900. And that's going to be 16,900. Okay. So your vertex here is 7, 16,900. So this is your maximum revenue. Okay, this is the number of X values. It's not $7. So now it asks us here, determine the maximum revenue and the ticket price that will give the maximum revenue. So the ticket price is from 12 plus 2X. So the ticket price will be 12 plus 2 times 7, which is 14, so $26 to give a maximum revenue of 16,900. Now you can also test it. Okay, so if that's going to be $26 times, we would have 1,000 minus 50 50 times 7. And we should get that maximum revenue, which we did. Okay, so that kind of confirms it. And then the next one is an area type question, another common maximum question. So it says a rectangular lot is bordered on one side by a stream and on the other side, 3 sides by 600 meters of fencing. So what does that look like? So there's your stream. It's a rectangular lot. Okay. Oh, that's not very good. Okay. So this is 600 meters of fencing. And it says determine the dimensions of the lot that will produce the maximum area. So let A be area. And then we want the dimensions. So you decide if you want to call the width W, and this would be length, right? So let W be width. And L be length. Okay, now we're going to have to express, therefore, 2W plus L equals 600 because of the length of those. We want to be able to express everything in just 2 variables. Right now we have 3. So if I solve for L here, I can get the length in terms of the width. So then therefore my area is length times width, right, which is going to be 600 minus 2W times W, and then expand it out and show it in descending order of degree. And now you can put it in vertex form by completing the square. Half of that is 150, so it's going to be plus 225, 0, so 22,500. After that, okay, and it says determine the dimensions that will produce the maximum area. So therefore, the width is 150 meters. Then the length, remember 600 minus 2 times 150. So that's going to be, the length is 300 meters. If you multiply those together, you should get 45,000. So 15 times 3 is 45 with 3 zeros. Okay, doesn't actually ask for the maximum area. Okay, to produce, you could put that in though, to produce the maximum area of 45,000 meters squared. Okay, so those are 3 very common application questions of quadratic functions.